Okay, so welcome to Unit 4, all about equilibrium. Okay, so what's equilibrium, what's dynamic equilibrium, what are all these terms? And I got you to do the definitions for these already, just using your textbook. But as with normal in Chem 30, very rarely do I ask you for a pure definition. It's more about an understanding or an application, right? So keep that in mind, that you don't have to memorize the definitions that you've just copied from your glossary, but rather understand them. You saw the word dynamic equilibrium in Chem 20. I don't know if you remember it or not, but you saw it. So dynamic means always moving, okay? And equilibrium, by definition, is the rate of the forward is equal to the rate of the reverse. Okay, well, what does that mean? Well, first of all, the dynamic equilibrium that you saw in Chem 20 was about, and you might want to draw this on the side here, it was about dissolving in a saturated solution. So if this is a saturated solution, let's just make sure that you can see that on the video. Can't really. There we go. If this is a saturated solution of sodium chloride, and that means that when I put this sodium chloride in, any more solid that I put in won't dissolve. Everybody okay with that? Everybody understands saturated? But the bit that I put in when it dissolved went and turned into a dissociation of these two ions floating around. So if this is saturated, then in my solution I have Na pluses and Cl minuses. Lots of them. Everybody okay with that? So here I have some NaCl solid, ion, 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 ion. Everybody get that? Okay. If I radioactively tag the nucleus, they've done this, they can do this. They make it an isotope with a heavier nucleus, right, an extra neutron, and you can watch it, okay? So with an instrument. So if I radioactively tag one of these Cls, this is a saturated solution, I add a radioactive NaCl solid. Oops, NaCl solid. Where should that NaCl solid go, radioactive or not? If this is saturated, what happens when you add a bit more salt to a saturated solution? Just goes to the bottom, adds to the pile. There it is. Let's make it green. Everybody okay with that? The pile just got a little bit bigger? Okay, but what they found is the radioactiveness doesn't stay in the solid bunch. And sometimes it appears out here. And then sometimes it appears back in. And then sometimes it appears out there. And sometimes it appears back in. So what does that tell you? If the mass of this pile never changes, that for every one that goes out into the solution, I must have had one crystallize back into my solid pile. For every one that dissolved out into the solution, I must have had two crystallize back into the solid. Have you seen those funny arrows before? Mm-hmm. So it's saying that I could go right, or I can go left, and I can talk about this. Now, that means dynamic. It's dissolving and crystallizing, dissolving, crystallizing, dissolving, crystallizing the whole time. That's dynamic. And equilibrium means overall you don't see a difference. This solid mass is the same. The number of ions dissolved is the same, as in number. But the actual ion is not the same. And the actual solid is not the same because it keeps changing. Does that make sense? Okay, so this is the example that you saw in Chem 20. Nod your head. There's only 5 of you in class today, so come on. Nod your head if you're with me. Shake it if you're not. Okay, all right. Another example of an equilibrium would be like a hot air balloon floating. How do hot air balloons get up in the air? Please tell me you know this. Hot air rises. So they light the little fire, warm up the air in the, right, and up it goes. And when they shut the fire off, because they do shut the fire off, right? The air cools, and what happens to the balloon? Goes down. So instead of going like a yo-yo, up, down, they can maintain an equilibrium where they turn it on, turn it off. Turn it on, turn it off. the air is cooling and the air is heating. Both are happening. Both are happening. But what you see is a stationary balloon. Okay, it's moving. There's a lot of dynamic equilibrium. Hot, cold, hot, cold, hot, cold, because the guy is turning the button on, off, on, off, on, off. Anybody been in a hot air balloon? Oh. Right, I've been in one that's tethered as well, but I mean like up. Yeah, no, me neither.
That's so scary. Yeah, no.
I know. I'd be a little bit like.
Yeah, I freaked out. I used to be floating up there in the balloon.
In London, you can like get a champagne picnic and go on one and go floating around.
What?
Yeah, but kind of cool.
That's cool.
But I think I'd be so scared I wouldn't be able to eat. Okay, so anyway, that's the end. Right, dynamic equilibrium. Got it? Okay. Homogeneous equilibrium. What did you find out for that definition? What does homo mean? Same, and genius means like a mixture. So what's a homogeneous equilibrium?
Same mixture.
Of what though? Okay, you look at these. Really, you wrote the definition. Thank you. You wrote the definitions. Really, you just.
Can I signal if you want us to look at it?
Yeah, look.
Okay.
Okay. See how these states are different? Solid, aqueous, aqueous. This would be a heterogeneous equilibrium. So the states are different. Whereas our homogeneous equilibrium would be like the hot air balloon. It's gas and gas, hot gas, cold gas. It's not really a chemical reaction equilibrium, but it is an equilibrium. Did you get that? Okay. Are you okay? Okay. Right, law of chemical equilibrium, what did you guys find? We're going to study this a lot today. That an equilibrium has a constant.
Ratio.
Pardon?
It's a constant ratio between the concentration of the products and reactants.
Good. So there's a constant. We're going to give that constant the letter K for each equilibrium that you find. There's a constant K. And that is equal to a ratio or a quotient, in other words, like a division, of your product concentrations divided by your reactant concentrations. Okay? And the quotient will never change. Is everybody okay with the word quotient? Do you use that? Yeah, okay. So the quotient will never change, the division between these two. But the numbers might. Like if I had the total product concentrations multiplied together to give me 6, and the reactants multiplied together to give me 3, then overall my K value is 2. But there's a lot of ways to make 2, other than 6 and 3. I could make it 2 and 1. I could make it 12 and 6. I could make it 0.5 and, right? There are lots of ways to make 2, but the 2 remains constant at a given temperature. At a certain temperature. If I change the temperature, I change the K value. At a certain, temperature.